Good morning, dear participants. Today is the fifth day and the last day, first session. Today we have with us Dr. Deepak Joshi from Sardar Vallabhbhai National Institute of Technology, Surat. He is an assistant professor in the Department of ECE there. He has done his PhD from IIT Gauhati. His research areas include analog circuit design and optimization, meta-heuristics, CAT for VLSI. He has many publications in reputed journals. So I would like to hand over this session to him so that he can deliver his talk. Thank you. Sound is not coming, Deepak sir.
Yes. Thanks for the reminder. Okay, so hopefully it is audible now. Okay, so thank you for inviting me, and it is really nice to present something in Guwahati, since I remember that we had, as a student, I joined. I was there participating in some course, which is scheduled by EICT technology, EICT, IIT Gauhati in Gauhati University at that time, and they were teaching cadence and analog system design from schematic to GDS2. So I was present with my colleagues there, and it was really nice experience at that time. Okay, so today this particular talk, hopefully this it is visible. The screen is visible at your end. Okay, so I am sharing with the two devices. So bear with me if I have done something wrong in that case. Okay, so okay, now it will be clearer. Yes. Okay, so I have been going through this whole schedule of this session, and I found that very interesting and prominent uh, figures were there to provide to give a lecture on the analog issues, analog design issues. Professor Sau was there from Kharagpur, so quite an interesting talk at the time. Okay, so hopefully most of the participants, although I received the list, but I just wanted to ask that how many participants are you really working on analog design, or you are here for achieving some scope of interests in this design or in this field, so that you can start research, isn't it? So there may be both of the motives can be there. Okay, so here today we'll be presenting about the techniques of optimization and algorithms. Optimization algorithms which can be applied to analog design. Okay, so generally how we design any analog circuit. Okay, so it is generally designed through, let's say, first of all, we have some set of specifications. Okay, some gain will be there, bandwidth, required bandwidth will be there. Similarly, there can be other parameters which are required of the design for the design. Okay, so let us, what particularly designer will react to all these specifications. So he will have to, first of all, he will have to choose the topology, isn't it? Let us say some system is demanding that this much of amplification should be there and this much of the noise figure they have been allowing. Okay, so accordingly they will have to choose the design, choose the topology, that what should be the topology of the circuit which will be best suitable for this design. Okay, and then he will size the circuit. Okay, so generally what happens that we start with pen and paper and we just find out that because 5 6 transistors are there, so we approximately decide that what should be the size of, or what should be the W by L ratio of any circuit, or the design circuit to be designed. Okay, so what happens that it takes a lot of time and efforts of the designer. Okay, so what happens that you have to tweak all the currents, and then you will have to tweak the W by L ratios of the transistor, so that in order to achieve the correct operating region, whether it is in saturation or linear mode, you will have to, accordingly, you will have to tweak the W by L ratio. All we can do is that we can regulate the current from a transistor, isn't it? So this current regulation means that we will have to select the width of the transistor in such a way that it should have some particular amount of drop across the drain and source terminal, so that it can be working in a required region of the operation, whether we are requiring it to be working in, let's say, saturation region or linear region. So this particular exercise takes a lot of iterations. Okay, lot of iterations means that first you will tweak it in the CAD tool, maybe it is in LT Spice or on the other CAD tools, Cadence and commercial tools are there. Okay, so you will see that whether you are getting the correct curve or not, or if at all you are not getting the curves, then you will go to its operating point situation, and you will find out that which transistor is in which region. So it is generally provided by the tools. You will get a file, and you will see that, you will be able to see that which transistor is in the active region or saturation region. Of course, it is active. Okay, so, and finally what happens that finally we decide that, okay, this much of sizing is suffice, and it is we are fine with that particular size in order to achieve our specification and performance of the circuit. So then it goes to the next stages, such as designing the layout and finding out the issues and correcting them, and then we'll go further for the tape out procedure. And before tape out, we will have to do some Monte Carlo simulations also in order to decide about the yield, isn't it? So the analog, particularly this design procedure, the roughly, I have told you the roughly what should be the procedure of design for the final tape out, but most important part is design itself, and designing the first design, or finding out the first cut design. Generally, it is called first cut design. So first cut design is basically what, from where you start on the paper, and then you find out, okay, so whatever the first design or first W by L ratios you put in the tool, that is the first cut design. And from that first cut to the final design, it takes a lot of efforts. So if we are able to apply some of the algorithms or optimization algorithms in order to minimize that particular time and efforts, so it will be very good, because it will be a great help to the designers, isn't it? So although in the smaller circuits it may not be visible, the reduction of efforts may not be that much visible, but let's say analog to digital converters and other complex circuits, so they takes quite a time. Okay, so, and even the reference circuit has to be designed, and so we are trying to minimize the manual efforts. Okay, so ultimately right now what I will be presenting will not provide you the best result. Okay, but it can give you the idea that from where we can start. Okay, so although this designing procedure is quite a knowledge centric procedure, that if a designer is experienced a lot, so the value of his work will be very high. So at the academia, or whenever we are starting, wherever we are starting to learn the design procedure, then it will be very helpful for us so that we are able to reduce our design efforts or the manual efforts in order to achieve the first cut design. Okay, although people have presented in literature quite times, quite frequently, that they are able to achieve even the even better than the first cut design. Okay, or even uh, right away you can fabricate from that design without checking the layout issues, or because they have incorporated those issues in the same optimization procedure. Okay, so then again, they have developed their setup of this optimization algorithm, and then they are applying more better models of the transistors that are being used for the fabrication. Okay, so let's start. So I was just trying to introduce the topic. Okay, so we'll be going like this. So the outline will be that first I'll try to just introduce you, maybe because some of you may be new, or maybe at the introductory stages of the optimization algorithms. Some of you might be expert, but bear with me because I will be just providing you the basic introduction, and then we'll see that the application in analog circuit design, and then we'll see that what are the difficulties that you can say that I have faced, and how we generally avoid such difficulties by improving the problem statement of our optimization problem. Okay, so the need of optimization problem is clear here, that if the circuit is getting more complex, okay, so it will be difficult for us to design it manually, and a lot of variables are incorporated in such cases. So it happens that by incorporating optimization techniques, we are able to judge, or we are able to decide that in which direction we will have to increase some particular W and increase or decrease some particular width of the transistor. Okay, so there are different algorithms which will be, you might all be familiar about the nature inspired algorithms, or evolutionary or swarm based optimization algorithms. So most of the engineering and the real life problems, they are applying them, and they are trying to find out some solutions. Okay, and then we'll go for the application in the analog circuit design. Okay, so utility of optimization techniques is quite clear that by using these techniques, we can achieve some direction from in which direction we will have to work in order to design the circuit. Okay, so why in analog circuit design? So why actually analog circuit design is very much important. Okay, so here I have got this figure from some of the literature. I will show you the reference later on. Okay, so in in this particular figure, it has been shown that why analog design is being a very small, covering a very small area on chip. Even then, it is taking a lot of effort. So you can see that the percentage of area acquired by the digital block in a particular SoC or the system is very high as compared to the analog block, but the efforts are very large for the analog. Why it is so? Because let us say in digital design and digital blocks, you might have been familiar that multiplexers are being used, adders are being used. Okay, so ultimately you will have to design a cell, or let's say one adder you have designed, and that the same adder will be used throughout the device or throughout the system. So you can reuse those blocks. Okay, so that is why even if this digital circuitry is acquiring a lot of area, okay, so but the efforts are less because you will have to design that particular cell once, and then you reuse those cells. But it is not the case with the analog circuits. Although analog circuits are like 15 or 20 kind number of transistors will be there, but it seems to be very smaller as compared to the digital counterpart. But then you will have to separately or particularly you will have to design every transistor at whenever it is required, because let us say, just take the example of amplifier. In the initial stages of the receiver, some low noise amplifier will be there. That same low noise amplifier cannot be used at the later stages because the gain will be smaller, but it will be required at the earlier stage because we will have to reduce the noise from that signal which is being received from the transmitter. Okay, so these are the things that the same, let's say, the amplifier cannot be same in all of the stages. Similarly, the other circuits, filters cannot be same, and mixers cannot be same. So they have to be designed separately. So that is why it is taking a lot of time. So analog IC blocks and then digital IC block. Okay, so that is how they differ in the approach. Okay, so now what generally we do is in the analog circuit design, when we will have to first represent it into the optimization problem. Okay, so generally, okay, so I'll just write it here that let us say in any optimization problem, what exactly is done. Okay, so there will be a cost function. That we have to minimize or maximize. Okay, so that cost function will be there, and then there are certain constraints. Okay, some constraints will be there, a set of constraints will be there. Let us say 2, 3, or any number of constraints can be there on the variables which are being used in the cost function. Okay, so now this is a mathematical problem here, and we will have to either we will have to minimize it or maximize it, isn't it? So this is the general format, the most basic format which is used by the optimization algorithms. And now we will have to represent our analog circuit in this particular form so that we can solve it. Ultimately, when you are trying to design on pen and paper, let's say with the help of pen and paper, the first cut design of any analog circuit, what happens that you have been provided some gain, okay, and then you will write an expression of gain, isn't it? Let us say for the basic amplifier it is GMR, okay, and okay, you can see that GMRD. Okay, so GMRD is some number, let's say 100. Okay, and you will represent this GM using the square law in the form of W by L, and then you will have a power required VDD times ID, isn't it? So from there, the power dissipation might be given, let us say 50 microwatt is the power. Okay, I'm just taking the typical numbers, maybe they may not be realizable, okay, just for the example. Okay, so VDD is confirmed for a particular technology, let us say 180 nanometer technology, we can take it 3.3 kind of or 1.8 volt kind of VDD can be considered. Then we can find out the ID here, and then from ID we can find out some relation between W by L here and some relation from the W by L here, and ultimately we will have to solve these mathematical equations for a particular transistor. Similarly, similar exercise have to be done for the other transistors also when we are not using the optimization algorithm. But the same mathematical solutions, ultimately we are solving a set of equations, isn't it? So that set of equations can be solved with the help of optimization algorithms. Okay, so that is what we are doing here, that we have to consider our cost function first of all, and then we will have to construct our constraints. Okay, so in which, what are the boundaries, or what are the limitations of the performation set? Let us say, what is the W maximum and minimum W can be there, and what is the maximum and minimum length of the transistor is possible. You can get it from the technology. Let us say, for 100 nanometer, it may be, you can consider it as L is equal to 1.8 or 0.18 nanometer, and then similarly, these there can be the constraints related to the power dissipation, and then slew rate can be there, and then if the operational amplifiers are there, so you can have the phase margin and gain margin as a constraint, because ultimately you can represent all such expressions in the form of WL and I, isn't it? So ultimately the variables are, let's say, ID, W, L. So these will be the variables. Okay. So is it? It is not moving, I think. Okay. So maybe it will come maybe in some time. So if I'm not audible, please tell me, because I seen that there is some network issue here. Okay, so if, as far as it is audible, then we can go. I'll just reshare it again. Okay. So this is a mathematical program of the any generalized analog circuit. Let us say you can have gain or power dissipation here. Okay, and then there are the many constraints which are in those constraints. This particular design has to be, this particular cost function has to be contained. Okay, the cost function has to satisfy all these constraints. Okay, so now we will go to the what are the available techniques for it. Okay, so let us see that nature inspired algorithms are there, and then there are the classical methods, and there are some machine learning and deep neural ANN methods are there, which are being used recently. Okay, so these are the three basic classifications of the analog design optimization methods. Okay, so first of all, they have started with the classical methods, and then they faced problems, because what happened at the time that the number of constraints keep on increasing, and the algorithm they are generally being used, they are generally using there, could not get converged at the time. Okay, so such algorithms are, let us say, steepest descent method. Okay, steepest descent gradient method is there, and then similarly there are interior point method is there. Okay, so what happened at the time, generally any optimization algorithm, it requires its, in the, for the classical, we are talking about the classical method right now, it requires that it should be, the cost function should be in the convex form. Okay, so it has to be convex optimization. if let us say it is not convex. Convex means that there should be only one drop in the gradient. Okay, so that can ensure that it is a global optima, global maxima, or global minima. Otherwise, let us say instead of a convex design, we have non-convex circuits. Okay, so let us say this type of cost function is there. Okay, so what happens that it optimization algorithm can trap in these local optimal solutions. Okay, and then we could not get assured that whether we are starting with the right result or not, isn't it? So that was the problem, and then the solution was there that we'll have to represent our cost function in the form of in such a way that it can be representing a convex optimization problem. Okay, so what happens that in order to represent it into the convex format, we will have to approximate, or we will have to ignore some of the terms which are making any objective function non-convex. Okay, so so in the process of ignoring or neglecting some of the terms, error introduced. Okay, and it restricted designers to further use such algorithms which have these restrictions of being the cost function in the form of convex function. Okay, so at the what happened that they shifted to the nature inspired algorithms. Okay, so nature inspired algorithms are such as particle swarm optimizations are there, and then genetic algorithm, ant colony optimization, river flow dynamics, and the hybrid of such methods. Simulated annealing is there, and we make the hybrid because even in the cases of nature inspired algorithm, although it is not a mandatory situation that we have our objective function in a convex form, but what happens that even they can stuck in the local minima. There may be the issues of conversions. Okay, it may not be converging. So it can keep on iterating the solutions, and it will not be converging. Then, so these are the some of the basic problems which are associated with the nature-inspired algorithms also. Okay, and let us say in case of genetic algorithm, the setup which we are requiring. Okay, setup means that the representation of analog circuit in the required format, mathematical format. So the setup should be easier. Okay, otherwise we will stuck to the this operation research part. So that will again restrict us to design the circuit. Instead, we are designing now algorithms. So there are the divergence. Okay, so there are disturbances of such kind. So the setup of the analog circuit should be can be done. It should be able to be generalized, or it should be scalable. Okay, we can increase or decrease the number of transistors, so it should be scalable. And let us say, because let us say you will not be designing every time your setup for each circuit, isn't it? So let us say you are designing one basic differential amplifier, then now you have to design the operational amplifier, or let's say OTA should be there, so it should be designed. So it is not a feasible idea to design. First of all, you design it, and then you optimize your circuit, and then you will play with these variable with these achieved results on the CAD2. Okay, so otherwise, so that is the main reason that these algorithms could not get popular in the industry that much. Okay, although they have some of the algorithms, definitely they have some of the automatic algorithms which are being used in the digital design part. they are using the same technique of min-max, finding out the minimum and maxima. Okay, but for the analog circuits, we are still missing that chain. Okay, so some of the difficulties are associated with this representation of analog circuit into the mathematical program format. Okay, so that is one issue. And then further, if you have represented it, now there can be the issues of getting it converged, or whether it is converging in a long time, okay, whether it is converging on the local minima or not. Okay, so these things has to be ensured. So there are, we have also some presented some of the hybrids, so that we can use the properties of the separate algorithm, so that one can converge faster, other cannot, other can avoid the local minima and maxima. So we made a hybrid out of these two, and then we used it on the analog circuits, so that we can ensure that whether we are not we are converging, and then we are avoiding the local traps. Okay, that was the idea of developing the hybrid methods. So there are a number of methods which are already being introduced by the researchers in the literature. You can found. Okay, so further you can say that there are the methods which are using the learning based methods, okay, which are using machine learning or deep neural network, DN and ANN they are using. So they are using on the basis of the database they have. So ultimately in the machine learning you will have to develop a good amount of database, isn't it? So it should be trained. The algorithm has to be trained over such data. So that is quite difficult for a introductory researcher or a beginner, so that and generally people have not kept this database in the public, as we can see that there are image processing applications of the machine learning, and you can find a lot of database on the internet. But in this particular field of analog circuit design, researchers are quite conservative, you can say that. They are not putting their database on the internet, so that it can help the community. But ultimately, if you are trying to, one of my MTech student has tried to initialize this database, and then they trained the circuit on it. So it took quite a time to just start the research, and then their MTech got over, because the time is limited, and they could only apply such algorithms of deep neural network in only on basic circuits which have already been applied. So it takes time. So if we have some research group which is working on the machine learning algorithms, so then it is very nice, because you can train your algorithm, you can improve you can have some modification in the algorithm, and then you can again train it, and then you can find out the results for a different type of circuits. So circuit to circuit database has to be there. So it is quite a restriction there, but once it is developed, let's say for some organization have some of a large number of, a variety of number of circuits are there, and then a good database is there. So it is always easy to find out the elementary solutions for the circuit design. Ultimately, we are trying to find out the elementary solutions only, because the circuit design also has some limitations. So now we are talking about the limitations related to, we have talked about the limitation related to these algorithms or the representation of the circuit into, so that these algorithms can be applied. But now let's think about, okay, so let us think about the limitation from the analog perspective, analog design perspective. Okay, so what are the manual limitations which are there? Okay, so let us say you are designing one very basic single transistor amplifier in 180 nanometer. You might be, I have gone through the schedule, so Mr. Sarfaraz, Dr. Sarfaraz is taking the hands-on session of LT Spice, I think. Okay, so in that you might have experienced that a lot of tweaks should be there in order to achieve the required output. So let us say now instead of 180 nanometer, you are going to the, or even in the same technology, let us say you are now having two stacked NMOS. Okay, one has NMOS and then another NMOS. Now the lower NMOS can be directly, the body can directly be connected to the ground, but not in the case of upper one. So in the upper one, you will have to consider the body effect. Now the expression you are going to use manually, the mathematical expressions, or you can say the relations of GM and the square law changes, if I mean to say that. So now you have to take body effect into the account. Okay. So similar situations are there when there are more number of stacked amplifiers are there, and it is very hard to predict the size manually. So, and then even you are complicating your mathematical model of the circuit, isn't it? You are introducing odd powers instead of square, and then although it is algorithm who has to solve it, but still we are complicating it, and there may be the issues with the convexity and the local traps. So such are the limitations from the designer's perspective, from the analog design perspective, that if you are having more complex circuits or on the lower scale, let us say instead of 180 nanometer, you are trying to design something on 65 nanometer or lower node, then it will be again a problem. And again, on the same technology, you are trying to design for the higher frequencies. Okay, so the same expression will be more complicated now. So such things are to be taken into the account. We have to be very careful about the application of these circuits, even with the optimization algorithms, because whatever we are feeding to the optimization algorithm, that will be providing the results according to that only. And if we are feeding the wrong model or the wrong equations into it, then how can we get the right answers? Okay, so we'll have to keep in mind that whatever the models, if we are using it correctly, so whether we are using it correctly or not, that has to be kept into mind. So I think there is some hand raised. So if you have any doubt, you can ask right now. So instead of, let's say, the question and answers at the end, we can discuss these right now, because many of the things which I am saying may not be written on the slides. So although it is on record, but right now you need some, if you have some query, you can ask. Okay, so let's move towards the next slide, which is a set of, let's say, the same things. It is a procedure of the design which we have already discussed, and then similarly the same thing also has been discussed. So here is the example, let us say. So example of a very basic low noise amplifier now. Okay, so whenever you go for the study of the low noise amplifier, so this circuit might be it will be very readily available. It will readily appear on the search of the low noise amplifiers. Okay, so the constraints on the right side in the table, you can see that the constraints and how these constraints are generally. Let me zoom it so that you can have a better view. Okay, so you can say that the input matching is there. So it is a good way to represent the constraints because uh, they can directly be fed into the optimization algorithms. Because what happens that let us say this is your cost function right now, your gain, or even let us say instead of gain in mostly we can consider that noise figure can be your cost function, let's say noise figure. So you can represent the noise figure or you can write the noise figure relation in the form of these variables, isn't it? GM will be there and the constraints on, from here you can get the constraint on inductor. Okay. So this is a type of mathematical representation of a low noise amplifier. Okay, I could not incorporate the noise figures expression, but it is quite large. So it is not a good idea to keep it here, but you can find it in most of the textbooks that for the initial technology nodes or for the larger technology nodes without considering any effect, you can still have some of the formats of some of the representation of these low noise amplifier. Okay, so this is one way to represent it, and there are another way or the more accurate way you can say that instead of using this square law, so we tried with the curve fitting also. Okay, so there is one thing that is called curve fitting. Okay, one practice to generate expressions. Okay, so let us say if you are aware of that some function is there which is let us say y is a function of, let's say, current and then w and then l. So there has some function and then you can have some curve from the simulator. At least you can start with the simulator so that we can find some better results. Okay, so what we do is that we get this curve from the, let's say, EDA tools, and then let us say some curve is there. Okay, and then you have to represent it into mathematically. Okay, so having all these constraints, all these limitations, we have simulated it once and simulated the circuit once, and then we got this relation. So this relation, if we are able to take out in the form of some mathematical relation, so we can use that relation directly in the optimization algorithms. So they will be more accurate than the earlier square law. Okay, so the GM now can be represented into the A1. Let's say some constant is there, and then uh, W raised to power some alpha 1, L raised to power some alpha 2, and ID raised to power some alpha 3. So these alpha 1, alpha 2, alpha 3, and A1. So these are the coefficients which need to be extracted from the curve. Okay, so this is the curve which is the nearest, which has the nearest fitting, or it is almost overlapping the curve which are generated by the simulator. So in simulator, we generally think that it is notified that a lot of complex models are being used. So they take most of the effects into the account. But for the beginners in this area and for the designers who are using it for the manual calculation or for the initial design, so they can use such functions also instead of square law to get the better or more accurate results. Okay, so that is also a one way to mitigate or to avoid the inaccuracy which is introduced by the short channel effects or by the avoidance or the neglecting of some of the terms, so that we can avoid the local traps, because such functions, they are in the form of polynomials. Okay, so there will be one term, polynomial. You can look it into the literature. It's quite a mathematical term. So it is the positive polynomials. You can say that it is made up of the two terms, positive polynomials. So these polynomials will be providing, will be, if we use these polynomials or other, let us say, other constraints are also in the polynomial form, so we can have a convex system or convex function to be optimized. So in such way, we can ensure that we are not going to be trapped in the local optimal solutions. So now this polynomial, if you want to go into more detail, so I can just refer you one paper, okay, which is by Thomas Lee. Thomas Lee is their well-known author for the CMOS RFIC designs, and Thomas Lee is the co-author. Actually, some first author will be some of his student maybe, but in that particular paper, it is in the 2000. It is published in the 2000, and you can go. It is about the operational amplifier. Okay, so operational amplifier design using uh, using geometric programming. Okay, so quite an interesting paper. Okay, and similar paper, similar in the same volume of the journal, similar paper is presented by Professor Pradeep Mandal, Professor P. Mandal from IIT Kharagpur. Okay, and in the same, both of the volumes. So maybe by coincidence they got the same thing, almost same thing, same representation of the operational amplifier in the form of mathematical constraints and cost function, and they both of them have solved it using geometric programming. Okay, so that is there. Okay, and you can start with, if you want to really go into the representation of the circuit in the mathematical program, and then you can, and this polynomial terms, it is quite frequently used there, and you can start with this particular paper, and then once you are confident that how to represent a circuit in the form of, in such mathematical form, then you can apply various algorithms which are available, various nature inspired or even geometric. If not geometric programming, then you can apply many algorithms. And if some of the teachers are still in the talk, so I can suggest that they can give their a course project type of assignment to the students to apply the very basic particle swarm optimization and simulated annealing or ant colony optimization in order to get the original results or the near accurate results. Okay, so because what happens that with this exercise we can have a framework which can be developed at the institute level, and then we can further inquire, or we can further improve it according to the requirement. Improvement means that whether are we able to hybrid some of the algorithms, other algorithms into the earlier one. So if the hybridization is possible, we can do that, and we can apply it on the more complex circuits, and we can apply it according to the incorporation of more complicated effects into the account. Short channel effects can be taken into the account in such cases. So for that, initially we will have to develop some base there, which can be easily developed with the help of students, because they are not, what I can see recently, that they are not very much interested in the designing, but they are very much interested in the programming. Okay, so we can use their programming skills, and we can direct them what to design and how to design. So combinedly, it can be, we can get some good results. So this is what I realized during the research, that okay, so it is just an advice. I mean, you can certainly use more better ways. Okay, so now let's think about the types of results we want. Okay, so one optimization result is basically, you can say that we are going to get a one design. Okay, one point or one vector. You can say that one vector. I need a optimal vector. Okay, so that is the output of a single objective optimization. Single objective means that you have only one objective. Let us say you are trying to maximize the gain, okay, but which is subjected to the power uses, which is subjected to the bandwidth, which is subjected to the limitation provided by the technology node, isn't it? So in such optimization methods, they are providing a single output. Okay, they provide us the single output, and then we can maybe cross check it on the CAD tool, and we can proceed in the design after that. So this is one way. But what happened is that in the analog design, it is not quite frequent, or that only single objective optimization is required. Okay, so what happens that when we are trying to, let us say, minimize the noise figure for low noise amplifier, then you can easily found that the gain is reducing drastically. Okay, you cannot take the any minimum value, you cannot minimize to any value, because there are some competitive constraints also. There are some competitive cost functions are also contradicting cost functions are there. So in order to deal the contradicting or the competitive cost functions, we have to go for the multi-objective optimization. So which is quite frequent in which is quite a frequent requirement in the analog design, because what happens that when we are trying to maximize gain, we are losing more power. Okay, so now we have to design for the lower power and the higher gain. So how that can be possible? Because they both of them are the contradicting cost functions. So in order to address such issue, what happened that let us say instead of one point, now they are looking for a set of points. Okay, let us say on one axis we have gain, on one axis we have power dissipation, let's say. So, and let's say we are trying to, we have the output of in this form, okay, or not even in this form. Let's say we have some of the points like this. We have received a set of solution now. So this set of solutions, when it is plotted on the cost function plane, this is the cost function plane because on both the axis cost functions are there. So this particular curve which we are trying to get, or which we are, by joining them we can see that. So this particular curve is called Pareto function. Pareto surface can be called Pareto. Pareto solutions can be, it can be called. Pareto is one Italian he was one Italian scientist who has introduced this term. So Pareto plot, you can say, Pareto function, we can be said. Okay, so this is the output of the multi-objective optimizations. And now someone can ask that if we were trying to optimize it, we were trying to optimize our circuit to get a particular first cut design, isn't it? That was from there we have started. And now you are saying that you have 5 results. So isn't that contradictory from the earlier statement? But no. Why it is not? Because let us say for a particular gain and a particular power dissipation, we are looking at. Okay. So this point is the most optimal solution in these situations. Okay, that is the idea of the Pareto point or the Pareto solution. Let me repeat it, that if we have a certain amount of gain which has to be required, and let us say we are trying to maximize the gain with the minimum power considerations. So we have taken one point here, that this much should be the power we should take into the account. And then we have taken this projection here, and the nearest point, with respect to that nearest point, we have got this particular gain. Okay, so this gain will be the best case for the given power dissipation, and this particularly point, actually this point is nothing but the vector which is having a set of W1, W2, W3, or the current, okay, set of the design parameters. Okay, so each point, every such point is representing a separate circuit. Okay, so because they are representing a separate design vector, or design vector is nothing but a circuit, isn't it? So because the topology is same throughout this experiment. Okay, so now the importance of this Pareto front is that you can have a variety of power dissipation at your end, and you can find the optimum power, optimum gain, or the maximum gain, and also you can find that what should be the parameter of the design at that particular gain and the required power. So that is the beauty of this multi-objective optimization, and many good papers are there in this multi-objective optimization, and who would not have uh, heard about this NSGA 2, most cited paper in the history of, I think, engineering, or okay, so it is from the IIT Kanpur. Professor Kalyan Dev is there right now. He is associated with some USA in the university. I think in maybe in some US university. But the paper is this particular paper has been this technology, this particular algorithm, NSGA, non-sorted genetic algorithm 2. It has been applied to a variety of engineering problems, including analog circuits also. Analog circuit is a one application, but they have applied it to the variety of solutions, variety of the real life problems, including the biotechnology, including mechanical, chemical, whatnot. Okay, so similarly, there are more advanced algorithms are also there, and which are developed by the same group and the other groups. Okay, and now people have started to apply such algorithms for the analog design applications. Okay, so what happens that they take two constraints, such as in case of, let us say, in case of low noise amplifier, what we have experimented during my research during my PhD, that we have taken noise figure at the one end and, let us say, gain on the other end. And if we are trying to minimize this, we may not be able to get a good gain if we are trying to minimize the noise figure. Okay, because these are that is what the contradiction here. Competitive cost functions are there, which are associated in this low noise amplifiers design. So we may be getting some set of points for the Pareto optimal solutions. Okay, so and these solutions separately can be considered as a separate circuit or the separate designs. Okay, so that is what has been considered, and now the quality of, let us say, similarly the many objective optimization, first we discuss it and then we will go that how to analyze that whether we are getting the good results or not. Okay, we are able to apply it, our algorithm is converging, we are getting the near accurate answers, but how to qualitatively analyze that we are getting good results or the better, superior results than the existing algorithms or the other algorithms. Okay, how to compare the results with the other algorithm, that is what we will discuss now. Okay, so the many objective optimization is that when we are considering the more than 3 objective functions at the same time, these are the competitive objective functions. Let us say in power gain bandwidth, we are taking on the three axes, then instead of the Pareto front, we will be getting Pareto surfaces can be generated, and the points which are associated with these surfaces will provide the design with respect to the best possible scenario with the provided ranges of the cost functions. Okay, and this is also called the non-dominated solutions. Non-dominated. Okay, so the Pareto solutions are the non-dominated solutions. Non-dominated means that in that particular range, that solution is not being dominated by the other solutions. Okay, that is the most optimal solution. Okay, so which cannot be dominated by others. That is why it is called non-dominated solutions. The set of non-dominated solutions can construct a Pareto front. Okay, so that is one theoretical aspect of the multi-objective optimization. Okay, so now how to qualitatively analyze it, qualitatively and quantitatively. Okay, so in case of single objective, let's say, what happens that we generally iterate our algorithm. Let us say I'm running this particle swarm optimization in MATLAB or maybe in Python. Okay, what happens that we converge it once, okay, and we get some result. Now it has to be tested that what should be the standard deviation. Okay, if we are trying to iterate it for, let's say, 1,000 times or 100 of the times, that in those 100 times, how much deviation we are getting from a particular result, from a standard result. Okay, so that standard deviation should be very minimum. Why it is so? Why we are getting different results, first of all? Okay, because these algorithms are randomly generated, randomly populated initially. Okay, random population not there. If some of you might have gone through the genetic algorithms, then the population has to be randomly selected. Okay, so if the range of width is there, so we'll have to start with some particular point, isn't it? So what we do is that we, in that particular range, we generate a, let's say, 1,000 widths or hundreds of widths can be generated randomly, and then we test on those points. That's what this algorithm does. That it takes every such points and then put it into the objective function or the cost function and find out that whether it is better from the earlier one or not, isn't it? It is the way of iterating it and how fast it converges to decide that okay, so this is the best optimal function, or this is the best value of the cost function. Okay, so in such process, what happens that a search methodology is applied by the algorithm. So the searching methods are different for every type of algorithm. That is certainly there, but ultimately every algorithm is searching randomly. Okay, they are starting with a random initialization. Okay, so that random initialization may cause the difference in the answers of the two different iterations, because there might be the case that the algorithm could not go into the feasible, some part of the feasible space, where in the next iteration it is trapped in that particular feasible state and space, and it could not search on the other side. So from a one side, or from it can avoid some sides sometimes. So we will have to, what we will have to do is that we have to iterate it many times, and then we will have to find out that what is the standard deviation. Okay, so if let us say four different algorithms are applied, and you are saying that my algorithm is better than the other, or my algorithm is providing superior results than the other ones in the literature, then what is the criteria to decide? Okay. See, if you are trying to optimize, let us say fx is equal to x square plus y square. Okay. Ultimately, if we are trying to minimize it, the value is zero, isn't it? If x and y should be kept, so if x and y, let us say, vary from -1 to 1, so what would be the minimum value? Minimum value will be zero, isn't it? So this zero can be achieved by every algorithm, no issue. But what is the standard deviation and what is the convergence rate, that decides the superiority of the optimization algorithm. Okay. Similarly, these are the cases for the single objective optimization. But now, what about the multi-objective case? Okay. So in every case, let us say three algorithms we have applied, three different multi-objective algorithms have been applied, and then we receive some results. Okay, so Pareto fronts we have received in every case. So now this Pareto front has to be checked for the quality of the solution. So first of all, this Pareto front has to be dense. Okay, so the density is one quality factor, and then the diversity is also another quality factor. How diverse is the Pareto solutions which are acquired in the process of optimization? So diversity and density is one point, and then other methods are there in order to qualitatively analyze, such as hyper area and hyper volume are there. Okay, whatever the area which is bounded under the curve, under the Pareto front. Okay, so the diversity is there, and we have to decide the superiority of the algorithm or superiority of the results according to such parameters. Okay, diversity and density. Okay, similarly, in the many objective optimization, we go for the hyper volume, and the more dense as the more area which is being covered under the curve, and it should be more diverse. Okay, so these are the points on which we can have a on these are the points on which we can select a variety of select a particular algorithm from the pool of various algorithms which are already given in the literature, and then according these are the points on which we can improve the algorithm, that we are getting better diversity or not. Okay, so now let's go towards the recent challenges. That what are the recent challenges? So the applicability and the setup time. So time to set up. Setup time is that how feasible is to apply, how feasible is to convert your analog circuit in the format of optimization algorithm. Okay, and how easy it is to apply. Let us say, let's take the two examples. Okay, one is the particle swarm optimization, another one is genetic algorithm. So genetic algorithm has many variables such as mutation coefficients, many coefficients, and uh, it is more complex to apply as compared to the particle swarm optimization, that because the deciding factors are small in the PSO. Why it is so? Because in genetic algorithm, mutation has to be considered, and then crossover has to be considered, and then again and the number of generation has to be considered, what is there. So, and the representation into the digital in the genetic form, that is also important. So the applicability and setup time is a important challenge, important aspect to select the optimization problem in this case, in the case of analog circuit optimization. Scalability is another issue. Scalability means that if you are if you have confidently applied some circuit and got the results, and on a one particular algorithm which is developed by you, so whether other more complex circuits will be effectively applicable on the same algorithm or not. Okay, so let us say if you are proposing some algorithm, so that algorithm has to be scaled. It should be able to be to get scaled. Okay, so what happens that sometimes if the more number of variables are there, let's say more transistors are there in the circuit, so more variables will be there. So those number of variables are being tackled by the algorithm in the same way that when the number of variables were smaller. So that is the question here, and because what happens that if we take more number of variables, sometimes the algorithm may not converge. Okay, then there will be a problem. So it has to be programmed, or it has to be designed in such a way that it should be able to scale up or scale down to, because the many variety of circuits can be designed using the same algorithm or the same setup. And then further this realizability and the errors. So these errors are generally incorporated or introduced by the mathematical representation of the circuit only. Okay, so let us say if you are using this wire law, and it will certainly be not accurate or not realizable, and then what is the use of optimization algorithms if we are not getting the correct figures? But it can provide some picture to, or some judgment, some point of judgment to the designers, that from where they can start. Okay, and then reliability means that let us say after the optimization you get some number, some odd number of bits which is not possible to physically design. Okay, so how to make decision in layout? Let us say you have got 0.18 nanometer size, and let us say you have got 0.20 nanometer size of W. Okay, so it should be able to be the results should be able to differentiate between these two, because okay, we are mathematically we are showing that this might be providing a better picture or better results, better gain, but it may not be possible to apply it or fabricate it physically. So there are, or it can throw some results beyond the limitations of width and length. So that is again not possible or realizable. So those are also the issues associated with these optimization problems. Because issues are there, that is why this area exists. Otherwise, if there would not have been any issue, so everyone might have used it so frequently. So issues keeps these areas alive. And recently, AI and ML with the existing algorithms, they are associated. Okay, so 2-3 basic ways in which they are applying machine learning. Okay, first of all, in order to produce better functions, okay, so let us say better functions, you can say, or better relationships or better models, you can say that better models. Okay, so in order to achieve better models of the circuit, and then using the same traditional method of applying it with the optimization algorithms. Okay, because whatever we are facing the difficulty with the errors due to the model of the mathematical model of the circuit. So can we avoid such errors? Okay, so we have seen one example of curve fitting, let's say. So curve fitting is nothing but the interpolation of these points and then judging about the same points. So there are papers available, okay, in which they are producing better models with the use of neural networks and machine learning. Okay, so and other way is that in order to select the topology, okay, so the topology selection can also be there. Okay, so topology selection means that if a certain specification is given, so we can train our model in such a way that it can select the topology. We can train our algorithm on the database, okay, whether it should use you can say that the telescopic amplifier format, or whether it should use the two-stage operational amplifier topology, what particular way in which we should design the circuit. Okay, so that particular decision of the selection of topology can be made with the help of machine learning and or other learning algorithms. And then the third one is that the exact leader design, that what is the set of sizes, set of widths can be achieved with the machine learning. What we will see that example in the next slide. Okay, so these are the recent trends, and robustness is also being incorporated. Robustness means that if there is a variation in circuit or fluctuation in the environmental issues, fluctuation in the environment, and then fluctuation in the power supply, how they can impact on the performance of the circuit, that is robustness, and those variations are also being incorporated in the objective functions and the constraints of the circuit. Okay, so if we consider those situations in our mathematical program, then we are able to generate more robust circuits. So this robustness is also you can find in the same paper which I have shown there. And Professor Pradeep Mandal has a variety of such publication uh, in his group, and so that they have also taken care of robustness of the results by using the optimization problems. Okay, so these are the two, three aspects of the future scope and on which the direction can be taken care of, that in which direction we can start working on. Okay, so let me take a quick break of 5 minutes, and then I will join with the another slide in which we will show. I will show you that how this machine learning is being used in the analog circuits. Doctor, Apurva sir. So I will be just taking a quick break of 2 minutes. Okay, so hope- I hope I'm audible right now. Yeah, you have changed some of the settings. Okay, so it seems that I'm unmuted now. And let's start with another some of the results and some of the papers which are already there in the machine learning area when we have used machine learning, some of the researchers, and they have successfully got the good results in the design of analog circuits. Okay, so let's start with this now. Okay, so machine learning is, as most of us are aware, because this is very recently it is popular so far in every field of the engineering, and this is just a procedure where we train our database and it judge on the basis of the training that what should be the number of what should be the value of variables with this with the existing database. It will compare it and then it will throw out the results. Okay, so there are some of the papers which are associated with this analog design. Okay, so you can see that a group is there in, I think, Portugal and Tunisia. They are there, and with this particularly, if you want to have a reference, so go with this name, Nuno Horta. Okay, so Professor Nuno Horta is working since long, and even in India, there are people in NIT Durgapur. They are working and they are publishing quite a lot in the area of Professor S.P. Ghoshal is there, and they are working in this optimization field. Uh, I have been following these publications since long, and you can see that the number of inputs are there for the ANN structure, and the technology is 130. They are being used. So sizing of the analog circuit. Sizing means that the finding of W by L ratios for every transistor. Okay, that is the size. And this particular optimization, you can say that, or the optimized sizing, finding out the optimized size is generally called the sizing. And deep learning and ANN are being mostly used for this. And different circuits are they are being using it. Amplifiers are being used. OTA and folded cascodes are being used. Differential amplifier. So these are the very basic and standard circuit for which we can come. Even we can compare our results with their results uh, if we are trying to optimize these circuits with our proposed algorithms. Okay, so a set of actually these particular slides are prepared in the last semester by one of my MTech student, and that is why you can you can see 21 here. Okay, so December 20, they may be in the date has been updated now. Okay, okay, so let's come back to these slides, and you can see that you can see that variety of trained technologies. You can the training is there on different technology, testing can be done on some particular technology. So what is happening inside it that, let us say, we are making, or we are simulating one circuit of, let's say, single transistor amplifier in 2 3 technologies. Okay, and we are finding out the results. Okay, now what is happening that, let us select one technology first. Okay, and then in that technology, by using ng spice, or you can say the lt spice, you can find out a variety of data. Why it is so? How it can be find out that you tweak the WL ratio, and you can fix the VDD, and you can find out a set of output. isn't it? And similarly, on the different technology, we can have the same tweaking. We can generate a set of database there. Similarly, on the other technology. So now we have, for the same topology, we have various variety of database. We have variety of data which are associated with the same circuit. Okay, in different technologies. Now we can train our algorithm on this database. Okay, so if so and so size has to be there, what should be the best gain? Which particular technology is providing the best gain? Okay, similarly, if let us say if some technology is already given fixed, okay, let's say out of these technology we are trying to optimize our circuit in 0.35 micrometer, okay, or 350 nanometer. So if this has to be chosen, then what should be the best gain which is already there in the data which is generated on this particular technology? We can choose the near accurate W by L ratio for that circuit. So that selection can be done on the judgment, on the basis of judgment, which is being generally produced by these machine methods. Okay, so ANN bring out the better results or the optimal results uh, of the analog circuits. Okay, so similarly, there are some more papers from TCAD, and so now you can see that the extended use of neural network models. So they are just training it on the different, and they are training their model, and they are generating it first, then they are testing it, and then they are producing the results. So this is the general flow of the working. Okay, so this particularly a overview is very much available. I think everyone might have seen that there are different layers, and then the connection of all the variables with every other variable of the layers, and then they have to ultimately decide about the final output layer. So this is the general idea of ANN, and then these are some of the signals activation functions are there which are being used mostly. Sigmoid and ReLU, they have been rectified linear unit. So we have used this particular function and activation function, and we have trained this circuit for this particular circuit. Okay, so now you can see that there is one two-stage operational amplifier. First stage is differential amplifier, another one is this common source amplifier, and then these are the design equations, very basic design equations earlier at the elementary application of machine learning for the analog circuit design. We are trying to excel in this area right now, but these are the elementary results which I will be showing you. Okay, so now this is the flow chart of that can show that how we have applied this this ANN in order to generate the better results. Okay, so first of all, the data is generated using ngSpice, which is open source, available to all. Okay, and then uh, we have trained it, and then we have, according to the requirement, we have found it, and then we have checked for the convergence. Okay, if it is not convergence, then increase the number of hidden neurons or hidden layers, and then it means that increase the number of relation between these two, between all the variables, and then it can be iterated again. Okay, so this the idea of the application of this particular ANN. Now we will go for, now this is, let's say, the initial size specifications are there, and then these are the input vectors and output vectors, what we are trying to get at the output, and these are some of the, because these are the paired transistors, so we have taken them same, considered them same. So activation function is this one, and the number of tests and this used environment, Google Colab. Okay, so most of the part is done by my student, but still I can, I'll try to explain it. Okay, so let us say here in this first table you can see that the input data for the training which is there, and then expected output is there, and set of initial widths are there. So now initial widths are also provided here, and then this particular setup is used for the data generation. And further it can see that, let us say, we are trying to increase the number of epochs, and means that the number of times the network trained with all the training data in one iteration. Okay, so if it is increasing that, I mean, the setup is being more complex, and we have to, it takes more time, you can say. Okay, and batch size is the number of training examples utilized in one iteration. Okay. So here the SPICE results of one of the test set. Let us say this one is considered for that, and so timing, you can see that the time of training are also written here. So if it is increasing, the time is also increasing quite a time, 3 hours. Okay, so these are the parameter specification which are further tested on the SPICE in order to cross check, and this is the input to ANN, this is the SPICE results. So we can have that somewhere, some of them are in good agreement, some of them are having a quite a distance, but these are some of the elementary efforts in this particular direction. So they can further be improved by using better models, I think. And because in GBW, we generally finds the disagreement, or we can say that the expected results have more parameters associated after we simulate into the SPICE. And even after simulation, I have seen that the measurement of the GBW after the fabrication, that is quite different, because the number of metal wires and their effects also being considered. So there may be the issues related with, and some random effects are there which cannot be modeled right now. But that is why this disagreement will be there. Okay, so, and the second table, in the next table, you can see that the inputs, which the widths which are uh, generated at the output end after the training network. Okay, so these are the results with the same design vector. We have generated some of the results here. Okay, and you can say that similarly CMRR and TSRR are also achieved. But although they are very elementary, but still a idea can be taken that how actually is, because in every paper it is written there that database has been generated, and but they are not providing actually the database. So that is the main constraint in order to start in this particular direction. So that is why it is, although it is quite exciting to go into this direction, but then again, it is very much hidden layers are there if we speak in the terms of ANN. Okay, so future work means that future work includes the number of improvements, which is that you can increase the matching rate, and short channel effects can also be taken care in this particular training, and uh, some of the targets are there. I mean, so some of the references are also given. I mean, you can start. They are very well written. You can follow this particular professor and Horta, and they have some of the very good books also in this particular field of analog IC sizing. Okay, so now I think we should go for the question answers, and if some of you might have been asking, okay, so let me check the comment section. Okay, please share the PPTs. Of course, I can share it, although the session is recorded, so certainly these recordings will also be shared to you. Okay, but I will send it to Apurva so that it can be distributed, but they are not very, I mean, very advanced slides. Actually, everyone of us are associated right now, stuck in the semester ending, so many of us are there. So I could have designed some better slides. Okay, so Apurvaji, you can. I'll just hand over this session to you, and we can go for some interaction and some question answer in this field on this talk. Okay, so if
Hello.
yes, Apurvaji. Okay, you are here.
If the participants have any queries, they can ask. Sir, can you share the PPTs?
Certainly, yes. I will send it to you on email or WhatsApp, whatever you say.
Okay.
Or should I paste it here? Is it possible?
You will better you give me. I will share it.
Okay, it is fine. I can send it to you. I'm just trying to send it right away.
Okay, thank you, Deepak Joshi sir, for your informative lecture. We'll be grateful for you. Hope for cooperation in the near future in the VLSI domain. So thank you, sir.
Certainly. I also invite the researchers or who are the beginners, maybe the experts, because I have seen Professor Mal was also there. So maybe he is here or not. I know. Right now he's okay. So some of the, if you want to associate it, get associated with NIT Surat in terms of, let's say, internships or other research works can be started in this direction, and we are very well open for this, for these opportunities. So although I try to keep it generalized, so that an overview can be given to the associated problems and issues related to the optimization of analog circuits. Okay, so it is that was the idea for in order to avoid the more technical details. because many speakers might have been in this particular program. They have been presented very well, and I also take references from them. So that is why I've chosen to just provide the idea that what are the problems which are associated with such applications. Okay, application of optimization algorithms in analog circuit design. Okay, so thank you very much, all the attendees, and thank you, Apurva sir, for providing us this platform to express our ideas. Thank you very much. Although some disturbances from my side because some repair work is going on, and so that was one disturbance is certainly. Okay. Thank you very much for listening me with this patience.
Okay, thank you, sir.